All right. In question 2, what we see is a force versus elongation graph. You've done this before in lab. You've also done it in the simulation now here. When you hang heavier and heavier weights off a spring, you get a linear plot. And if you fit the slope of that line, you will get your K value, or it's better known as the spring constant. Looking at that graph, it's pretty easy because it goes to the origin. So if you wanted to do rise over run, the rise goes all the way up to 24 on that graph, and then the run ends at 0.4. So basically we would have 24 over 0.4. That's our slope. That's our rise over run. That's our K value. So 24 divided by 0.4 gives us a K value of 60. And if you recall the units for spring constant, it's newtons per meter. Now what we have here is we've got a spring that we pull back and it's let loose, and it goes between, or from here to here, past the equilibrium point, and then back to here and back to its original point. And this will happen over and over and over again. We're told that this distance here is 0.25 meters. This is 0, that's the equilibrium point. This is negative 0.25 meters. So we can see that it oscillates back and forth between these two extremes here. First thing question asks us to calculate the spring constant from the graphical information. So that's what we did right there. Just getting the slope of that graph gets us our spring constant. When we pull it back and allow it to oscillate, they ask us for the period here. We're also told here some key information here. The mass that's attached to it is a 0.50 kilogram mass. What you should have seen in our demo that we did on video was that the mass that we attach to our spring definitely affects the period in this case. Unlike the pendulum, the mass definitely matters here. And if you think back to the formula, T is equal to 2 pi square root of m over k here. So a lot of people think about, well, where do I put in this information that we pull it back to 0.25 meters? We don't. We should have seen in that demo and in the lab simulations that that doesn't affect the period. It doesn't matter how far you pull it back. So it's a little counterintuitive that way, but let's look at our math here. 2 pi. I got 0.50 here, and I've got 60 here. So running through the math, again, what we're going to do is not leave our answer in terms of pi. And I'm going to get a period of a little bit more than a half second, 0.57 seconds here. After that, would pulling the spring beyond it affect its period based on that rant I just said? It's no. It is independent of it. And the last question, what if we attached a larger mass to the spring? How would that affect the period? So again, let's write out the formula here. What you find here is that m is in a numerator here. As long as it's in a numerator, as m goes up, t goes up. And that's not a direct relationship because there's a square root here. What we're going to find is that larger values of m will give you larger values of t. And you can put a larger number in there and prove to yourself that, because putting in, let's say, 1 kilogram in there, you're going to get a larger value of t. Based on the formula. The spring constant doesn't change. It doesn't matter what mass you attach to it. This K value is set in stone for this particular spring. So a larger mass will increase the period. And then conversely, a smaller mass will decrease the period. Now it's entirely possible to swap out a different spring and get a different period as well, but in this particular question, the only thing we ended up changing was the mass.